Hello. So this will be the last video in this lecture, and I'm going to introduce a different approach to the joint hypothesis testing and a different approach to construct the F statistic. But the resulting F statistic is equivalent to the previous F statistic, so it is just another view to understand F statistic and the hypothesis testing. So let's think about a regression model with exactly 3 regressors. You may consider more than 3, but for simplicity, I'm only considering 3. So suppose that there are 3 regressors. You can imagine student to teacher ratio, expenditure per student, and percentage of English learners. And the hypothesis you'd like to test is that beta 1 equals to 0 and beta 2 equals to 0, which implies student to teacher ratio has no impact on the test score, and at the same time the expenditure per student has no impact on the test score again. So it is a joint hypothesis, involves 2 parameters. And we are going to consider an interesting idea. So now suppose that your hypothesis is correct. If you believe that your hypothesis is correct, then these 2 variables are useless. You don't need to include these 2 guys in the regression model because they are 0. If you believe that, you don't need to keep them in your regression model. So you may simplify the regression to this case, right? This is the restricted model. So the general regression model is restricted by the hypothesis which you believe in. So then it is easier to estimate the regression model, and actually easy to understand what's going on. On the other hand, so we call this the restricted model, and on the other hand, the original model is called the unrestricted model. So you know what they mean. So unrestricted model and the restricted model, we are going to estimate both regression models, and we'll compare how they differ. And based on the comparison of those models, we may conduct the joint hypothesis testing. So I'm going to just call this model U, model R, so unrestricted and restricted. And then, in general, think about the goodness of fit, how well the model predicts the outcome. In general, the unrestricted model must be better in predicting the outcome than the restricted model, because the unrestricted model utilizes more variables, more regressors. So adding more regressors does not do any harm, even if they don't do any good, but they don't harm. So the model U, the U can do better than R or at least as good as R. That is our basic idea. So in general, the R squared, which represents the percentage of explanation by the model, must be greater for the unrestricted model than the restricted model, right? And now, additionally, assume that if the hypothesis was correct, and then actually the dropped variables are not helpful in predicting Y, because beta 1 will be 0, beta 2 will be 0. So these 2 variables are useless in the unrestricted model. So as a result, the performance of unrestricted model and the restricted model must be similar to each other, because x1, x2, it doesn't matter whether they are included or not. So if the hypothesis was correct. So if the hypothesis was correct, their R squared, the percentage of explanation by the model, must be similar. So the performance by R and performance by U must be similar because their difference is 0. Therefore, using this idea, So in general, this is better, but they are similar when the hypothesis is correct. That implies that you can reject the null hypothesis if the difference is large. So you can tell if the difference is large, then you can tell, oh, it is not correct. So that is another way to construct a test statistic. And in our example, so think about this, the same thing, exactly the same thing, but let's put the labels like in a concrete example. So in this case, as you see, we are interested in these two variables, student to teacher ratio, expenditure per student, and we assume that beta 1 is 0, beta 2 is 0. So these two variables, if the hypothesis was correct, then these two variables will be useless, 0 and 0. So you may drop them from the regression model. So this is the restrictive model. And the number of restrictions here is 2. The degrees of freedom is 2 because you are restricting two parameters, beta 1 and beta 2. So the number of restrictions is 2. And the fit of the model will be better in the unrestricted model because even if they do not have any explanation power, but they don't do any harm. So will be better or at least as good as the restricted model. So exactly this is how we are going to construct a test statistic, and the formula is like this. So R squared, unrestricted R squared, must be greater than restricted R squared. So if you take the difference, this is positive, and this is the difference between restriction with restriction and without restriction. And first, divided by the number of restricted parameters, Q, and then denominator has some weird like formula, but you may understand it as the standardization portion, just to make the distribution stable. So it is not, we are not going to be considering. So then the basic idea is, if the numerator is big, then the hypothesis is likely to be wrong, and then in that case, F will be large. F will be large, so you need to reject the null hypothesis if F is large enough. And for example, in this example, so in this example, we can calculate R squared and R squared. These R squared are included in the default result. So you know them, and we also know how many variables the unrestricted model has and how many restrictions we have, and then plug in the numbers and we obtain an F statistic. By the way, so this requires, so the advantage of doing this is that the R squared is automatically calculated from Stata. So instead of typing additional command, you may run two regressions and compare their R squares. So it could be easier especially when the regression becomes more complicated and when the hypothesis becomes more complicated. However, another problem here is it assumes that everything is homoscedastic. So it assumes the homoscedasticity assumption. So the result is actually different from this guy, because this guy is using robust standard errors. So this result is true without like, even if the homoscedasticity is wrong, but in here this may be wrong if the homoscedasticity assumption is wrong. So but it gives you another intuition what we are looking for and what we are doing. So So summary, this is homoscedasticity only F statistic. So it's only for homoscedastic model. And in many textbooks, this is introduced as the only F statistic, but there are alternatives, but still it is widely used. And also, in the end, this F statistic equals to the F statistic given earlier. Then, and we know the distribution is chi-squared divided by q. So, and remember, it is homoscedasticity only F statistic. And all the theory follows from the earlier results. The threshold and the distribution are the same. Okay, I will call it a lecture. So in the next one, I plan to finish this chapter so that you can prepare for the midterm exam. Okay, thank you for watching and see you later. Bye.